this today's lecture, we are looking at coordinate transformations for Euclidean spaces. So we will understand what coordinates are, what transformations are, and what Euclidean spaces are at the end of the class. And we'll be able to do some transformations. But there are several issues that will come before that. Last week, our main task was the all-important Einstein summation convention. We moved from the regular use of the summation symbol, sigma, to the use of repeated indices as an indicator of summation. Noted that this method does not alter the meanings of expressions, but helps us gain parsimony. You could have still put the summation signs there, but they now are no longer necessary. Observed rules governing its applications, especially how to distinguish between dummy, that is mutable indices, as distinct from free indices. If you remember that dummy indices tell us how many additions, how many things are summed over the place of addition, whereas free indices indicate the number of in the equations that you are going to have. If you have one free index, that's one. That is one free index will give you no free index. That's one equation. That's 3 to the power 0. That is non-free index. If you have one free index, that's 3 equations. That's 3 to the power 1. If you have 2 free indices, that is 9 equations. That is 3 to the power 2. If you have 3 free indices, that's 27 equations. And it just goes on like that. If you have 4 indices, that's 81 equations. And those 81 equations could just be in a single expression. And you will have that many equations. The free indices give you the number of equations. A single free index is 3 equations in 3D space. How many equations are 2 free indices? I've already told you what they are. We also learned to know if there are errors in index notations. For instance, if you have a dummy index repeated more than once, that is a problem. And if you have a free index that is not existing in every, a free index must exist in every expression, every term in an expression. Every term must have a free index. A free index must be common, whereas dummy indices don't have to be common. They are just indicating summation on the term that it's present in. And if there is double summation, you need to have 2 different dummy indices on that. I want to remind the class that it is not just convenient that you go to the chat room to ask your questions. It is compulsory that you participate. And it is the chat room, I'm saying it is the chat room that is going to help us to know that you are participating in the class. That's number 1. Number 2, there are 5 marks for participating in the chats. And we take a record of all the participations every lecture. We have everything. We have the data. We do analysis of the data. So students who do not participate in the chat room are going to score 0 out of those 5 marks. And if that is the difference between passing and failing, you have yourself to blame. If that's the difference between having a good grade and a worse grade, you have yourself to blame. So there is nothing stopping you from participating. By participating, I do not mean that you answer questions correctly. Just participate and show that you are awake, and that shows, let me just see that you are interested in what's going on. 2 major symbols were introduced, the chronicle delta ij, which you remember whose value depends on the relationship between its 2 indices. When they are explicit and equal, the value is 1. When they are explicit and unequal, the value is 0. When they are not explicit, then we just leave it as a variable. The Levi-Civita 3-index symbol, epsilon, alpha, beta, gamma, whose values depend on the uniqueness and arrangement of its indices. 1 when they are unique in the arrangement of 1, 2, 3 in an even permutation, -1 when they are in odd permutations, and 0 in any other case. Again, the summation convention is still valid. Time did not allow us to cover the entire scope Were we to express, we were to express using the newly found power with the summation convention, Kronecker delta and Levi-Civita, the component forms of vector operations. We will do more of that today. We are going to remind ourselves what scalar product is. We already know that. We already know multiplication by scalar product, vector product, and we will now introduce the tensor product in this class. We will expand on these things. And what you now know about scalar and vector product, the way we express them here, make virtually all the theorems you learned in your elementary days trivial. When you are told to find the terms of a tensor, of a vector product, you just write it out. If you are to prove some vector relationship, just write them in the index notation, and those proofs just come almost trivially. So this is a far more advanced way to learn this matter than you are used to. We start with dot product. Recall that EI dot EJ. Remember that instead of I and J and K, we use E1, E2, and E3. If we call it EI, I goes from 1 to 3, or EJ, J goes from 1 to 3, we are still saying the same thing. So EI dot EJ is delta IJ. If the I and J are equal, it will be 1. Let us E1 dot E1 is 1, E2 dot E2 will be 1, E3 dot E3 will be 1. In those cases, IJ are equal to 1 or 2 or 3 in each case. When they are not equal, like E1 dot E2 will be 0, E2 dot E1 will be 0, E1 dot E3 will be 0. All of those expressions are found in this single. So I want you to go to the chat room and tell me how many equations this represents. How many equations are here? This expression, go to the chat room, tell me how many equations there are there. I'm looking in the chat room, and this is a very good question for the class. And let me tell you that I've looked at all the answers, and only Warith Ogunwolu and Emmanuel Adenekon know what they are doing. The others are giving the wrong answer. What my question is, how many equations do we have in EI dot EJ? Now, those of you who know there are 9 equations there, I want you to now write those 9 equations for me. Now write what the 9 equations are. Write it out, because the others that don't know, they need to be taught this. And I want to see the 9 equations. Type them. Let us move on. All those people who said there's only one equation are wrong. There are 9 equations. Is this class awake or asleep? Okay, let me begin. E1 dot E1 is equal to 1. That's one equation. E1 dot E2 is equal to 0. That's another equation. E1 dot E3 is equal to 0. That's another equation. E2 dot E1 is equal to 0. That's another equation. E2 dot E2 is equal to 1. That's another equation. E2 dot E3 is equal to 0. Say good. E3 dot E1 is equal to 0. E3 dot E2 is equal to 0. Then E3 dot E3 is equal to 1. So when you have that equation, when you have the equation we just looked at, this single equation is actually representing 9 different equations. Is that clear to the class? Because you all failed it except 2 people. And even those 2 people did not even know what the equations are. I want to know whether that is clear or you still have difficulty with that. Because if you do not understand that, we are wasting time going further. This is a result of the summation symbol. I want an answer from the class. Is that clear or is it not? Okay. I want more responses because there are so many people with bad answers or poor answers who don't seem to know. And I'm waiting here because it is important that I'm carrying you along. There is no point pretending you are doing anything else if this matter is not clarified. It's very important. So you can see that anytime we have 2 free indices, it means in 3-dimensional space, we are dealing with 9 equations. If we have 3 free indices, we are dealing with 27 equations. Please bear that in mind because I'm going to keep asking. Okay, so now consequently, if you will now have A dot B, you know that we can write A as A1 E1 plus A2 E2 plus A3 E3, which is this one. This one is A1 E1 plus A2 E2 plus A3 E3. This also is B1 E1 plus B2 E2 plus B3 E3. When we take the dot product, you know that one thing I want you to know. Multiplication is always multiplication. The same rules apply. The only thing is that if the vectors are not commutative, then you just always maintain their position relative to the symbol. I will explain that later on. But apart from that, any scalars that are in the product can be moved around. You know, in my second equation here, where I say AI EI times BJ EJ is equal to AI BJ E1 dot EI dot EJ. You can write AI and BJ anywhere in this equation and you'll be correct. But because EI dot EJ is delta IJ, because it is delta IJ, and you remember the nature of the summation, the nature of the chronicle delta, it is a substitution symbol. When you use the substitution power of it, you can come here. So you now have A1 B1 plus A2 B2 plus A3 B3. That is, and this is something you already know from your elementary vector analysis, that A dot B is just simply the product of the relative terms, so sum together. This is the proof of it here before your eyes. So it's no sweat on it. Very easy. So dot product in the component form, very easy to find. Note that on this line, we avoided having 4 indices of the same type by invoking the fact that a dummy variable is mutable and you can use any other symbol. If I and J are not available, you can use alpha, beta, you can use any other thing to make sure that in an expression, a dummy index is not repeated more than once. Otherwise, we would have written AIEI dot BIEI. If we did that, then you have a single expression with 4 i's, which would have been wrong. Last week, again, we went this far. Last week, we looked at A with E1. We looked at the fact that E1 dot E2 is E3, E2 dot E3 is E1, E3 dot E1 is E2. You know this from your elementary vector analysis. I cross, sorry, it's not cross, a dot, it's cross. I cross J is K, J cross K is I, K cross I is J. But you don't need to take me, you don't need to believe me, work it out. Remember that the dot product, a cross product of two vectors is the magnitude of the two vectors, magnitude multiplied by each other, multiplied by the sine of the angle between them. We have worked all these things out here, and we have worked them explicitly. And when we work them explicitly, we worked out EIJK, and we found out that whatever value this one attains, it is exactly the same value this one attains. When this one is minus E2, this one is also minus E2. When this one is E3, this one is also E3. When this one is E1, this one is E1. When this one is E2, this one is also E2. When this one is 0, this one is 0. When it is 0, it is 0. When it is minus E3, it is minus E3. When it is minus E1, it's minus E1. When it is 0, so what more profit do you need for me to bring to you to tell you that this quantity here and this quantity are equal? So because of that, we have this, we do not have any further proof of the fact that EI cross EJ is the same thing as EIJK EK. So I'm going to ask you a question now. Two things. How many equations do we have in this? The first question is, how many equations do we have in this expression? How many equations? The second thing is, how many terms do we really have on the right-hand side? How many equations do we have in that expression? And in each equation, how many terms do we have on the right-hand side? You need to, these things must be clearly understood by you before we can move on. So go to the chat room. So let me see whether you fail it as you fail the other one. How many equations do we have, and how many terms on the right-hand side? David Akinola, you failed again, but it is good that you tried. I'm more angry with the ones that are not trying. Okay, Agbutesho, think, okay, Ogunwolu, 9 ensuring. Do you mean 9 equations or ensuring? Is that what are you what language is that? Consola, okay. Chukwalu, Ogunwolu, okay. Ogunwolu, I understand you now. We have, okay. So you can see, why are there 9 equations? Because there are 2 free indices, and why are there 3 terms? There is 1 pair of dummy indices, so that would give you 3 terms there. So you have 9 equations, and it's very important that we know what we are doing. That shows we know what we are doing. So we are here now. This is, remember, in the last something, we were looking at the dot product, and we're able to express the dot product. And I said the AIBJ can be anywhere. You can put them before the EI. You can put them after the EI. You can put them before the EJ. You can put them after the EJ. You can put one on one side. It doesn't matter, because a product, whether it is a multiplication by a scalar, or a scalar product, or a vector product, or a tensor product, the scalars that are inside that product continue to be like scalars, and their multiplication can take place everywhere, anywhere. That it is only the vectors that are there. In the case of the dot product, it doesn't matter, because dot product is commutative. It doesn't matter if your A dot B is the same as B dot A. But where we are now in cross product. You know that A cross B is not the same as B cross A. They are different. So at the same time, because the AI and the BJ that are there are scalars, they can move. You can bring the BJ on the far side and bring it to the beginning. There is no problem because a cross product is still a product. But the EI and the EJ must remain in that same order with respect to the cross product sign. The one that is before it must always remain before. The one that is after must always remain after. Otherwise, you have made a mistake. So we can write this. Remember that EI cross EJ is written as EIJK EK. So we can replace this product by EIJK EK. But the AIBJ can be anywhere, can be written anywhere there as we choose. There's no problem with that. So before we move forward, what we are going to ask you now is that I want to see how many free indices are in the last expression and how many dummy indices. The last expression on this page, how many indices are free and how many are dummy? How many indices are free and how many are dummy in that last expression? Okay, Daniel Sadiq, I can see you. Ogunwolu, I can see you. Fagbemi, I can see you. Good. No index text is free. Okay, so all the people that answered that question got it right. So I'm assuming that they are representative of the class. They are also representing those who will get 0 in the chat. Something later on. So it's okay. Now, the next thing I want us to do is very important. Now, there are, how many things are we summing in that right-hand side? How many things are we adding together on the right-hand side? How many terms are we going to add together on the right-hand side of this expression? How many terms? Emmanuel Adelekon, you are wrong. Sadiq, you are right. Somayiro Amifuna, you are wrong. Warit, you are right. So how did we get 27? Because there are 3 dummy indices, so it's 3 raised to power 3. Omoniyi, you are wrong. Abiodun Omoniyi, you are wrong. It's 3 raised to power 3. That's why we it's raised 3 raised to power 3. If there are 2 dummy indices, if there are 2 sets of dummy indices, it will be 3 raised to power 2. If there's 1 set, it will be 3 raised to power 1. If there are no dummy indices, it will be 3 raised to power 0. So that means that there is only 1 term. So a pair of dummy indices will give you 3 terms. 2 pairs of dummy indices will give you 9 terms. No, 2 pairs will give you 9 terms. 3 pairs will give you 27 terms. Okay, good. Now, the next question, which is harder than it. What strategy do we use to write these things out? If I tell you to write this thing out of the 27 terms, how many are non-trivial? How many of them are non-trivial? Again, chat room. How many of this how many of the number are not trivial? There are only 6 non-trivial terms. Frederick, you are wrong. 21 terms give us 0. Only 6 terms are non-trivial. And I hope you have your pen and paper with you. I will give you a trick to write them out just now. And you are not going to worry about the ones that are 0. This is how you are going to do it. You know that if I is 1, J and K, for this term not to be 0, J and K must not be 1. So J and K can only take the value of 2 or 3. So if I is 1, J can only be 2, K is 3, or J is 3, K is 2. So for I is equal to 1, K can only be, J and K can only be 2 or 3. Or another way to do it is to, first of all, write the 3 terms in K. Write just those 3 terms in K. EIJ 1, AIBJ E1. EIJ 2, AIJ E2. EIJ 3, AIBJ E3. So let me write it out. First of all, the first, what you do, I think this is something I should have. Let me see whether I would prefer to write it. You try and get those 6 terms, and you can be looking at what I am doing, because I'm going to be doing that. I'll create a fresh page so that I can do it the way you should do it. You shouldn't do it in a crude way, writing out the 27 terms. It's going to be very wrong. So if I want to express this, if I want to write this out, take it like this, copy. I can say this is equal to EIJ1 AIBJ E1. I want to distinguish between this E, which is a vector E, and this, the rest of it, plus, because we are summing over K, plus plus EIJ 2 E2. Plus EIJ3 E3. So we have 3 terms now. So we can now say it is equal to, so in this particular first expression, let us take I. First of all, notice that in the first expression, I cannot be 1, because if I is 1, the whole terms will be 0. So let us not consider. We can only consider I is 2. So we can say is equal to so when it comes to the value of I can only be either 1 or 2. So when I is, sorry, I can either be 2 or 3. So it can be 2 or 3. So when it is 2, J can only be 3. Because if J is not 3, there's not, okay. So in the second expression, so we can also have I is 3 and J is 2. That is all the terms that will be non-zero for E1. Every other term that will occur there will be 0. Can somebody tell me why every other term that will occur here must be 0? If you know it, go to the chat room. I will come back to look at it. And then I would come here and I will say, I will add this one. So if we are looking at E2, because this is already 2, that means that I and J can only be either 1 or 2. So we will write an additional expression for when it is 1 and when it is 2. Those are the only possibilities. So when since k is already 2, I can be 3 and j can be 1. I can be 1 and j can be 3. Those are the only two possibilities. And again, in the last expression, since k is 3 already, what do we have? We have that if k is already 3, I can be 1 and j is 2. And I can be 2 and j is 1. These are the only expressions that are non-zero. Out of the 27, these are the only 6 that will survive. You try it out, you will see that any other term you put other than these ones, you will have a situation where there are 2 equal numbers under the e, and you know that one will give you 0. So let me see if there's anybody in class that does not understand how this expression we have. Let me just make the expressions clear. Math, edit math text, math options. So align at this character, also align at this character. That's how you write it. These are the only terms that survive. I want to go to the chat room again and check. Okay, so agape. Is it clear to you now? Agape, agape, agape. Agape, I'm talking to you. Okay, it's clear. So you can see that even though there are 27 terms in that expression, we do not have to write all those 27 terms. We can selectively write the ones that are important to us, the ones that don't vanish. So we still have one more step to go. The next step is this. Oh, sorry. The next step is that this is equal to it is also equal to. Now, I want you to tell me, what is E231? Is it plus 1 or minus 1? Oh, sorry, I am wrong here. So I is 1 here. So this I here should be 1. And J is, sorry, I here is 2, sorry. I here is 2 and J is 3. I here is 3. I is 3 and J here is 2. I here is 3 and J is 1. I here is 1 and J is 3. Then here I is 1 and J is 2. And lastly, I here is lastly I here is 2 and J is 1. Okay. So 1, 2, 3, 4, 5, 6. Those are the 6 terms. So what I want you to do now, there are 6 positions. If you think the first one is 1, write 1. If everyone is 1, write 1, 1, 1, 1, 1, 1. If it is -1, you say -1, -1, -1, -1, -1, -1. If it is 1, -1, 1, you can say -1, 1, -1, 1. Just there are 6 things here: E231, E312, E31, E321, E312, E132, E123, E213. First of all, notice that they are all different. There's not one that is repeating the other, and they have values of either 1 or -1. So go to the chat room and show me that you know what these numbers are by writing all the 6 in a single sentence. 1, 1, 1, 1, 1, or 1, 1, 0, 1, whatever they are. I want to see your, in this, just make sure that your order is the order that I've written them here. So I'll go to the chat room and check you there. So let's see. We're being very busy. Okay. Marvelous. Are you still find it difficult to see the question? What are you not able to see? Want to see, can't see the question? Okay, let me go back and show you the question. Okay, question. What I'm saying is that you want to know is E321, sorry, 231. 231. So we can say, therefore, we have A2, B3, copy. And then minus A3B2, then 3, 1, 2. Okay, so you can see how, I mean, I'm sure this the final figure is familiar. You can see that this is what A cross B. These are the terms of A cross B. So you see that the first term is A1B, A2B3 minus A3B2. The second term is A3B1 minus A1B3. And the third term is A1B2 minus A2. No. There's something wrong here. It cannot be. It's 1, 2, 3. This is 1, 3, 2. A, 1, 2, 3. 1, 2, 1, 2, 1, 2. So it will be A2, 2, 1, 3. A2, B1, A3. It's A2, B1. It's A2, A1, B2, A3 minus A2, B1, A3. So if you like, you can write this now as you can have this one as equal to so which is this expression is what you are expecting for the cross product. You can get this from other means. But the beautiful thing about this is that all of that expression, all that long expression was hiding inside this simple thing. So this simple thing, so when you are working with indices, even though you might argue that it was difficult to get this, but you don't even have to. You can just leave your expression in this form because you know that this form contains everything that you need. And all the zeros and the non-zeros, everything is inside that form. If you will bother to expand it, you don't need to expand it. Just leave it there. That is the formula for A cross B. This is it. The component in component form, this is what A cross B is. And remember where it's coming from. It's coming from this identity that EI cross EJ is simply EIJK EK. Because of that, several things now become very easy for us to compute. So EI cross EJ is EIJK EK. So that is it. And we have proved in this on this next page that if you were to work it out, it will give you your familiar expression for the cross product. So that is what we wanted to do there. And before we go on break, let me just introduce the dyad. We will talk more about it when we come back. Now, we've already looked at multiplication by scalar. We've already looked at scalar product, and we know the components of a dot product. We know the components of a cross product. That's what we have just done. We know how to express these things in the index notation, and now we are now ready to introduce a completely new term. One exceedingly important object that you can also produce from taking a product of two vectors is a tensor. Naturally, we call this product a tensor product. But you remember, the other products we had aliases. What other thing do you call the dot product? Go back to the chat room and tell me, what else do you call the dot product? What else do you call the dot product, for instance? Okay, you call the dot product inner product. What else do you call it? What else? Scalar product. You call it dot product, you call it inner product, you call it scalar product. You are correct. Now, what do you call the cross product? What do you call the cross product? The cross product has other names. You call it vector product. You call it cross product vector. Does it have any other name? No. The cross product is not an outer product. Emmanuel Adenekon. Foul. The cross product is not an outer product. It is an inner. It's not inner or outer. It is cross product or vector product. Now, when you call it cross product, you are calling it that from the point of view of its symbolism. If you call something dot product because it is a dot that is used to express that product. Let me ask you, class, is there any other way to express the dot product apart from a dot? Is there any way to express the inner product apart from a dot, symbolically? Does anybody know any other way? Has anybody else come across a way to express the dot product apart from a dot? You don't know. Well, if you read wide enough, there are people use comma to express it. You put the two vectors in a bracket and you let comma separate them. So instead of A dot B, you just say A, comma B, and they are in bracket. There are other expressions. You put them in angle brackets. So there are other ways, but just know that when we are naming products, we either name them after the symbolism or after their product. When you call it a scalar product, what you are saying is that when the product is carried out, the result you get is a scalar quantity. That is why it is a scalar product. This other one, instead of calling it a cross product because of its symbolism, you are saying that when you do the product, when you finish doing the product, what you get is a vector. In the light of that, if we are going to, if I multiply two vectors together and I get a tensor, you can see now why we can call that a tensor product. That is, so one exceedingly important object you can produce from taking product of two vectors is a tensor. Naturally, we can call such a product a tensor product. But you can also use its symbolism to call it. The symbol we use is a circle with a cross inside it. It combines the product sign and a circle. So you can therefore call it a dyad product or simply a dyad. So there's something you can call a tensor product or a dyad product or a dyad. A dyad is defined. What is a dyad? A dyad is defined by what it does when it acts upon another tensor, another vector. For instance, if A dyad B, or the tensor product of A and B, were to act on C, this is what the result will become. The result will become B dot C, which is familiar, in the direction of A. You know this quantity is a scalar in the direction of A. Our time is gone, so I'm going to give you a 15 minutes break. And I want you to drink down the idea of introducing a new thing. I will talk about that when we resume. But I just want you to go on break with that information intact. So a dyad product is what you get when you multiply two vectors together and you get a tensor. Because of that, you call it a tensor product. What you get at the end of the day is a tensor. And that tensor, the way it works, the way it is defined is how does it behave when it is acting upon another vector. The way it behaves when it's acting upon another vector is that you take the dot product of the second object, the second operand with the vector, and the answer is in the direction of the first operand. So that is the definition of a dyad. We will now see the consequences of this definition after the break. So you can go on break now, and you come back exactly at 11:15. Please, I will start teaching at 11:15, so don't delay. Okay, so before we went on break, we just defined the dyad. The dyad is a tensor product. It is a dyad product, and it's also an outer product. So the dyad is called a tensor product, a dyad product, and sometimes it's also called an outer product. You will see the reason why as we move along. And what is a dyad? There is only one thing that defines a dyad: what it does to a vector. Once you know what it does to a vector, anything that does that to a vector is a dyad. If you have a dyad with two parameters, a dyad B, C is equal to B dot C in the direction of A, multiplied by A. So the scalar, and then that is the vector direction. And so that is not just in the direction of A times A. So it takes both the magnitude and the direction of A along with it in its product. That is what a dyad is. So what we are going to do, just like we have been able to express, remember that earlier in the class, we were able to find an expression for dot product in terms of components, AI, BI, A1B1, A2B2 plus A3B3 is the component form of A dot B. Similarly, the component form of A cross B is EIJK, AIBJ, EK. And by the time you express the 27 terms that are in there, you will get what you need as a cross product. It is easier, you will discover, than remembering any other thing. This is the easier way to do it. You don't need to work it out manually the way we have worked it out. It can take part in operations, just leaving it the way it is in the initial notation that you have it. When we get to the dyad, we say that A dyad B operating on a vector gives you this expression, and that is what defines a dyad. But the next thing we want to do, we want to see, can we put this dyad in terms of components of the vectors that are in it? We will try to do that, components of a dyad. Now, if you have A dyad B, a dyad is still a product, just like any other product. A is AIEI, B is BJEJ. As before, because a dyad is still a product, you can pack the scalars out of it, and what you are left with is EI dyad EJ. It looks like EI cross EJ. It just looks like it. They are just completely different. These are completely different beasts. For example, if it is EI cross EJ, if you transpose them, you get a negative. Here, you do not get a negative. There is no relationship between EI circle times EJ and EJ circle times EI. They are completely different dyads. They are completely different. So they do not have any sign relationship with each other. So that means that when you are looking for the components of a dyad, there are 9 bases. A vector has 3 bases, E1, E2, E3. A dyad has 9 bases, and they are E1 dyad E1, E1 dyad E2, E1 diad E3, E2 diad E1, E2 diad E2, E2 diad E3, E3 diad E1, E3 diad E2, E3 diad E3. Each one of those will have a component. So what I want you to do in this expression here, find me the coefficient of E3 diad E1. Go to the chat room. Tell me the coefficient of E3 diad E1, the coefficient of this one. I want that in the chat room because I told you every one of these will have a component. Tell me the component of E3 diad E1. So tell me the component of E3 diad E1. And then if you are back, they answer me. E3 diad E1. What is the component of E3 diad E1? What's the coefficient of E3 diad E1? Kayode, you are wrong. It's not -1. Akiola, you are wrong. Aha. Oguwolu, you are correct. It's A3B1. A3B1. Temiloluwa, you are wrong. A3B1 is the correct answer. Now, since you do not, I am not explaining anything, Akiola. I'm going to put another, I'm just going to give you another question. So what you are going to do, you are going to tell me the component of, you are going to tell me the component of another of the basis of the diad. Look at this expression here. What is the coefficient of E2 diad E2? What's the coefficient of E2 diad E2? And you can get that by looking at the first expression there. What's the component of E2 diad E2? What's the coefficient of E2 diad E2? Just go to the chat room and tell me the coefficient of E2 diad E2. Good. Now you are awake. Now that the class is awake. So because how did I get E2 diad E2? I just put I is equal to 2 and J is equal to 2. All you just do, just put I is equal to 2 and J is equal to 2. So David Akiola, are you on board now? David, let me see whether David is on board. Yes, David is on board. Good. So David, I have you with me now. So you can see that so there are nine components. There are 9 bases, and each base will have a coefficient, and you can get the basis. You can get the coefficient from the coefficients of the vectors. So if I ask you now, what is the coefficient of A1 diad E3? Okay, lastly, A1 diad E3. What's the coefficient of A1 diad E3? Coefficient of A1 diad E3. Good. So you are live to that now. Good. So let us move on now. So because we have done several things now, I just have these 2 pages, I think. Let's see how many pages. I have these 2 pages where we have, how many products have we done? 4. That is multiplication by a scalar. That's a product. Multiplication of 2 vectors as a dot product. That's another product. Multiplication of 2 vectors to get a vector. Multiplication of 2 vectors to get a scalar. Multiplication of 2 vectors to get a vector. And multiplication of 2 vectors to get a tensor. Those are 3 different products. That means that you cannot just tell me we are multiplying 2 vectors together. You can't tell me that because I will have to ask you, is it scalarly or vectorially or tensorially? Are you getting a scalar product or a vector product or a tensor product? If you say we are multiplying 2 vectors, you are being ambiguous, and we have to disambiguate with the sign. There are symbols for disambiguation. So you can see that on this page now, the first thing, alpha u, if alpha is a scalar, you can multiply alpha by u. it is clear what you are doing. Scaling a vector, multiplication by a scalar, there's no explicit sign required. Now, but it will be an error to say U beta V, even though beta is a number, is a scalar, because between U and V, there is no explicit implied product. We do not have a dot, we do not have a cross, and we do not have a dyad. So if once there are two vectors involved in an expression, you cannot just multiply them together without being more specific, because those three things have different meanings. One produces a vector, one produces a scalar, the other one produces a tensor. They have different meanings that cannot be reliably guessed unless you supply the needed information a priori. If you have two scalars, you can multiply them and just write them, just concatenate them. And everybody knows that alpha beta or beta alpha means alpha times beta. And there is only one meaning to ascribe to alpha times beta or beta times alpha. There doesn't have anything more than one meaning. You have two vectors v and u, and you just say vu, that's an error, because you have to specify which product you have in mind. Explicit disambiguation sign. Explicit disambiguating sign is required. We note that certain authors imply this simple concatenation as a way of representing the tensor product. There are books that have been written, and when they write two vectors concurrently together like that, they imply the tensor product, but that is not the current literature. Those are old books. The most current literature is that if you want to do a tensor product, you put a dyad symbol between the two tensors. In the most current literature of the subject, the tensor or dyad sign is the preferred way to represent this product. We retain that more popular convention here and subsequently. Now, suppose you multiply a scalar. We are now on this last line. Suppose you multiply a scalar by the cross product of two vectors. Of course, that is possible. And in that, the vector product of two vectors gives a vector. Multiplying this by a scalar does not require another sign. The order of the scaling is not important. So beta into A cross V is the same as beta U cross V. Beta into U cross V is the same as beta into U, beta times U cross V, or U times beta V. Is that beta U cross V, or U cross beta V, or U cross V beta? As long as you do not change the order of those vectors themselves, you are okay. The order of the appearance of the vectors is inviolable. If you change it, you are dealing with a different beast entirely. So beta times U cross V is not the same as beta times V cross U. And it's not the same as, although this second one is the same as V cross beta U, but it's not the same as U cross V beta. So just note that you have to be very accurate when you are dealing with these things. We can also, some people think vectors are matrices. Vectors are not matrices. Vectors are, and the reason why vectors are not matrices is that a matrix is essentially an algebraic construct, whereas a vector is a geometric construct. Vectors and tensors are geometric, whereas matrices are algebraic, but they are related. For instance, if you can have a row vector of E1, E2, and E3, and you have the column vector of A1, A2, and A3, the multiplication of them is A1, E1, A2, E2, A3, E3, which is the same thing as the vector A. So you can write them as two matrices, the matrix of the basis and the matrix of the components. Many times, that matrix of the components is said to be the vector. I'm sure you will come across books. You come across books that we write A1, A2, A3 and say that's a vector. Now, are they right or are they wrong? They say, or B1, B2, B3, I say that's a vector B. Are they right or are they wrong? They are wrong, but they are conventionally right, because if something is wrong and enough people are saying it, and then they are right, because just their share population. Just their share population. If you speak English, I will say because why? It's wrong, but in Nigeria, most people will think you are right, so therefore you are right. So that's the situation. Let me tell you the correct thing. The correct thing really is that if you write a vector as A1, A2, A3 as a column matrix, or you write it as a row matrix, you are making an assumption. If you write it as a column matrix, you are assuming that the bases are expressible as a row matrix, E1, E2, E3. If you write them as a row vector, if you write them as a row matrix, then you are assuming that the bases exist as E1, E2, E3. That way, you will get exactly the same result under those assumptions. But many textbooks assume you already know that. There's no need to be labeled that point. So they just write it and tell you that this is A1, A2, A3 is a vector. And they go on from there. When you go to artificial intelligence, machine learning, they do that a lot. They just write you a matrix and say that's a vector. And they can write a matrix and say that's a tensor. And I just want you to know, when they call a matrix a tensor or a vector, there is an assumption of a particular basis. If that assumption is not correct, everything goes haywire. And so I want you to bear that in mind. A vector is not a matrix, but a vector has a matrix form. A tensor also has a matrix form. So these are the two matrix forms of the vector A. And this is a matrix form of vector A. This is a matrix form of vector B, provided you are assuming that the bases here are a row vector and the bases here are expressible in a column vector. You see that when you do that, you are going to get exactly the same expression that we have gotten before. So when somebody writes a vector as a matrix, he's making certain assumptions. Similarly, if it's a dyad, this is what you mean, because the dyad here, the matrix form of the dyad is what you have in that matrix, but the basis can be written this way. And if you do the appropriate multiplication, you are going to get the same 9 terms that you have in your dyad here. There are several ways to get these same 9 terms. There are 9 terms here, as you can see. There are 9 terms in this expression because there are 2 pairs of dummy indices. So you can have 9 terms, which are the coefficients of all of this. You can write it out, and if you express it in this way, you can also get the same thing out. But remember that between the 2 vectors, whether they are written in matrix form or not, there must be that dyad symbol. That dyad symbol. So you don't just multiply them as if you are multiplying ordinary numbers. You must multiply them tensorially. So you must have E1 circle times E1, E2 circle times E1, E3 circle times E1, E1 circle times E2, E2 circle times E2, and E3 circle. You must have it like that. So between any two vectors in a dyad, there must be that symbol. There must be a symbol that disambiguates the product that you are implying when you are doing that with 2 vectors. You cannot just multiply 2 vectors together and go and sleep. You must tell us whether it's a dot product, which is a scalar product, or a cross product, which is a vector product, or a dyad product, which is a tensor product. Because when you multiply 2 vectors in that way, what you have created is actually a tensor. We are going into tensors gradually. Now, let us now tell you about something that is very interesting. The trace of a dyad. The trace of a dyad. The trace of a dyad. To obtain the trace of a dyad, you can write it in the way we have on the left-hand side. You write TR, which means trace, or the dyad A circle times B. It is the same thing as AIJ, the trace of, because the trace, you can just take the scalars out of it, because what you are really interested in is the base vectors. So you can just get the trace of base vectors by replacing the dyad product by a dot. If you replace the dyad product by a dot, you get the trace. And you can see that the trace of a dyad is simply the dot product of the 2 vectors. If you work that down, you see that if I have A dyad B and I want the trace of it, is simply the dot product between those 2 vectors. It is the inner product as can be seen from the matrix, the scalar product operands. If you write it out in matrix form, you will see that it is the diagonal matrix of the matrix representation of the dyad. Remember that in the previous page, we already saw the matrix representations of the dyad. We see the matrix representation of the dyad. That diagonal of it, the diagonal of it is the trace and is simply the dot product between two. So if you just replace the sign there by the dot product, what you have is the trace of the dyad. So when you are looking at tensor analysis, you will see that the dot product doesn't even really exist. It is just simply the trace of the dyad. And you will find out later on that even the cross product doesn't exist. There is another construct. So we can deal with all those things without even referring to dot product or cross product because they are all derivable from the concepts of tensors. So there's nothing, all that you have been doing in vector analysis are just a playground warm-up. The real map there is the tensor analysis. Everything there can be obtained as special cases. If you want the dot product, just take the trace of a dyad. You get your dot product back. So let us deal with a very, 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 very important application of the dyad. And to do with it, this is I will be slow here because even if this is all we do today, it is important enough and it is good enough for us to do it. Let us say you have three vectors I, j, k, which are the unit vectors of coordinates e1, e2, e3. We use these days. We stopped using I, j, k. Suppose we have another set of vectors. Now, this set of vectors, we call it zeta 1, zeta 2. Oh, no, sorry, not zeta now. This is xi 1, xi 2, xi 3. The pronunciation of this is xi, xi 1, xi 2, xi 3. Let us imagine that initially they were coincident. That is, E1 and xi1 were the same line, E2 and xi2 are the same, and E3 and xi3 are the same. And you suddenly rotate away, you maintain the same origin, but you rotate away the xi1, xi2, and xi3 so that they are now different. So that means that the xi1, xi2, and xi3, they still remain orthonormal. That is, they are still unit vectors, and they are still normalized, and they are still orthogonal to one another. So all you have done is that you have rotated them away from the position they were before. The question is this: if you had a vector inside this original system, what will the value of that vector be in the new system? If you can answer that question, you have done coordinate transformation by rotation. If you can answer that question, if you have the thing already in you had it initially in E1, E2, E3, and you now want to refer to the same thing in xi1, xi2, xi3, what would, if you knew the components in E1, E2, E3, and you know xi1, xi2, xi3, can you now find the components of that thing in the new system? If you can, then you understand what is meant by coordinate transformation by rotation. Rotation is not the only coordinate transformation. There can be other transformation. You can have coordinate transformation by reflection, for instance, and it is not a rotation. A reflection is different from a rotation. You can also have a coordinate transformation by translation, which is different. There are all sorts of you can have coordinate transformations that are neither rotation, mirroring, and translation are three types. There are so many other coordinate transformations, but we are going to look at coordinate transformations generally, starting with this. So consider the set of cardinal coordinates orthonormal vectors E1, E2, E3 as shown in blue figures. These vectors are position vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, I emphasize, I'm not meaning how many times you eat your food every day. If you like, eat 1, 1, 1 or 2, 2, 2. That's your palaver. I'm talking about the coordinate unit vectors. Consider another autonomous system shown in pink. I hope I got the color right. They said men do not know color. Me too, I don't know color. Whose unit vectors are oriented as shown? Let these unit vectors be xi1, xi2, xi3. All we know about the coordinate vectors is that they too are orthonormal, having the same origin, and you can look at them as a rotation away from the original one. We can now get a new system. We can express the new system in terms of the old. Set E1, E2, E3 are autonomous and therefore linearly independent. They form a basis. Therefore, any vector in their space can be written in scaled additions, linear of them. This includes each of the vectors xi1, xi2, xi3, because even though xi1, xi2, xi3 are now bases of their own and they are controlling their own space, but they too are vectors. So each one of them can be expressed in terms of E1, E2, and E3. So we can say xi1 is alpha 1 E1 because it will have a component on E1, another component on E2, another component on E3. They can be zero. They can, depending on how much rotation you have. So if we have that, we have 9 coefficients, alpha I, bi, and gamma I, where I goes from 1 to 3. So you have alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, gamma 1, gamma 2, gamma 3. These are coefficients to be determined. When we determine these coefficients, then we have been able to express E1, E2, and E3 in terms of xi1, xi2, and xi3 in terms of E1, E2, and E3. Suppose instead of alpha, beta, and gamma, we used a single index symbol A1, A2, and A3, so that alpha j is A1j, beta j is A2j, and gamma j is A3j. So alpha 1 would now be simply A11, alpha 2 will be A12, alpha 3 will be A13, and so on. So we can, why are we doing this? We are doing it purely for convenience. There is no other reason. There is no mathematical reason apart from convenience that's making us do this. You already know that once we do this, it will be easier to use the index notation, and we are going to be running after fewer demons than we will be running after right now. The number of demons here are too many right now, but we will now have to deal with only A's and A's and E's and Z's. Otherwise, we would have had to deal with A's, E's, Z's, alpha, beta, gamma, and all those things. We are reducing the number of variables we are running after. So if we have that, our original transformation equations can now be written as, can now take the form xi is aij ej. Scalar multiplication with alpha I, E alpha results in this. So you can see that the coordinates of these quantities, this A11, A21, and so we can find them. We can find them because right now this equation gives them. So AI alpha is simply xi I dot E alpha. So if we change alpha, if we write j instead of alpha, we see that xi I dot ej is aij. So this is actually what relates the two. It is this matrix that relates those two coordinates together. Remember what we started with. We are just simply trying to see how do we express these new coordinates in terms of the old. And we know that if we want to express the new coordinates in terms of the old, we need to find A11, A21, A31, A12, A22, A32, A13, A23, A33. If we can find it, and what did we find here? We found that if we simply multiply scalarly xi I with ej, we get aij. So if you want to get A11, you are going to multiply xi1 with E1. If you want to get A31, you have to multiply xi3 scalarly with E1, and so on. So that gives us everything that we want. If we want to do the reverse transformation, the argument that I have here proves that the reverse transformation is just the inverse of the matrix. So if you can find this matrix, And you are now asking yourself, suppose I want to express, suppose I start with xi1, xi2, xi3, and I want to express something now. Suppose this is the origin, suppose the original system is xi1, xi2, xi3, and then the new one is e1, e2, e3. How do I transform e1, e2, xi1, xi2, xi3 to e1, e2, e3? Just reverse the process. That reversal is simply the inverse matrix. So if you can find this matrix, the one that does the reversal of the process is shown by this argument to be the inverse matrix. And I do not want to go into that detail. You read it up on your own. And if you have questions, post it on the web and I will answer you. So what we are saying here is that in this particular situation, the matrix of transformation can be found by just taking dot product of the respective unit vectors. And the matrix here, if you want to reverse the transformation, all you need to do is to take the inverse of the original matrix of transformation. The question I have for you again is, how many equations do I have here? How many equations do we have in this expression? Again, ladies and gentlemen, go back to the chat room and tell me the number of equations here. In order for you to answer, you have to check how many dummy variables are there, how many free variables are there. So that would help you to know how many equations we have. So I'm going to see you in the chat room now. Daniel, you are wrong. There are 9 equations because there are two free variables, 2 free indices. There is no dummy here. There's no dummy because there is nothing repeated in an expression. Nothing is repeated. For there to be a dummy, there must be a repetition inside the expression. Okay, so I've explained that. I think let me just move on now. So most of you understand it now. So let's go. So this is where we prove that the reverse transformation is the inverse. We can write this in the matrix form. Road sign. In the next 5 slides, we present a 2-dimensional view of the geometry of the transformation of coordinates. This is tedious, though not rigorous, and you need to be patient. What we are trying to achieve here is for you to believe the easy formulas we will later use. When we shall have established the connection, we will not need to repeat this tedious process again. However, those who did not give sufficient attention will find it hard to apply. I am changing my mind here. In previous sessions, I always taught this geometrical interpretation. Instead, I'm going to just give you the answer because the answer is easy. I have convinced myself the answer is easier to follow. So I am omitting this geometry. I'm just trying to give you the geometrical interpretation of the transformation of rotation. But instead, I will just go and explain what happens. So if you just take a look at what is happening here, if you are moving from the e's to the x's, all you need is this dyad. If you are moving from the x's to the e's, all you need is the reverse dyad. So the rotation dyad is this. And you will see that if you do this and you use it to transform the e's, you are going to get if you are moving from e to xi, if you are moving from e to xi, you are going to have to use this dyad of transformation to get the answer. So the transformation tensor is the transformation tensor between two autonomous systems is simply E. If you are moving from E to xi, is simply E circle times xi. So, I'm sorry, the transpose of it is E circle times xi. So if what you if you have difficulty in knowing what to do, just remember that the one that comes first is where you are going. For the transformation, the one that comes first. So this EJ circle times xi j is transforming from the xi to E. If you want to transform from E to xi, it is now xi circle times E. So the transformation of rotation can be, you can rotate from the east to the xis. You want to rotate from the east to the xis, it is xi circle times E. If you want to rotate from xis to the east, then it is E circle times xi. It is where you are going that comes first, and then where you are coming from comes second. If you use that on the original vectors, you will see that the answer gives you the expression in terms of the new one. So the new one is what comes first because of the nature of the dyad product. Remember, let me just go back and show you. Remember that we define a dyad. If you have a dyad, this is the definition of a dyad. It is that if a dyad operates on a vector, the answer is the dot product of the two that are near each other in the direction of the first one. So at the end of the day, is whatever starts the dyad that is going to be the new coordinate system. So it is, so if you want, there's nothing you can miss here. If you are doing a rotation from one system to the other, and you want to find the rotation tensor or the rotation dyad that is going to make that happen, what you are going to do is that you are going to take the unit vector where you are going, and you are going to take its dyad product with the unit vectors coming from. If you do that, you are going to get the rotation tensor that you need. And the formula is simple. Where are we going? If we are going to the E systems, then let me just go back now to the equations we had. Let's see it again. Okay. So what we are saying here is that this one gives you the rotation from the xis to the east, because where you are going is the east. That is what you get. The rotation from the xis to the east. So, and you can see that this is E1 xi1 plus E2 circle times xi2 and E3 circle times xi3. That is the dyad sum that you are going to have. And this one will give you all the components that you want straight away. So the dyad gives us the rotation vector, the rotation tensor that we can use to operate on the vector. So remember that we know how a dyad operates on a vector. We know, because if you have a dyad and it's operating on a vector, this is the formula that you are going to use. This is how a dyad operates on a vector. That looking at the dyad, this is the only formula you need to memorize, and it is not hard. If you have a dyad operating on a vector, the answer is the dot product of that, the second operand of the dyad with the vector you are operating on in the direction of the first one. This is the formula. So the question I want to ask the class now is this: when a dyad operates on a vector, like vector C, what is the nature of what you have on the right-hand side? Is it a scalar? Is it a vector? Or is it a tensor? Go to the chat room and tell me. If a dyad operates on a vector, and this is the answer, that answer, is it a scalar? Is it a vector? Or is it a tensor? I'm going to the chat room to wait for you. Is it a scalar? Is it a vector? Is it a tensor? Okay, most of you got it right. Emmanuel Adeneko, you got it wrong. Who else got it wrong? Emmanuel Adeneko is wrong. Oyi Consola is wrong. What you have is not a tensor, it's not a scalar, it's a vector. This quantity here is a vector because B dot C is a scalar quantity. When you multiply a scalar by a vector, what do you get? It's a vector. Multiplication by a scalar doesn't change the nature of a vector, because B dot C is a scalar. When you multiply by A is, if A is a vector, the answer is still a vector. So when you operate a dyad on a vector, you get a vector. And that is not just true of dyads, it's true of every tensor. When any tensor operates on a vector, it gives a vector. So if the definition of a tensor is what transforms a vector to another vector. You can see that the magnitude and direction of the vector you are transforming is different from the vector you get at the end. Because the vector on this, the vector that you started with is C, but the vector you ended with is on the direction of A. So they may not be related at all. But this is the formula to get the transformed vector from the vector you are transforming. So I think that is where we're going to end it today. I want you to reread, when you read the notes, if you have difficulties with what to, the only thing that I didn't prove too much is that I just told you that the rotation tensor, instead of going through the rigmarole, there are two ways I proved it, but you don't even need to prove anything. Just know that if you have a system from where you are coming from to where you are going, you want to get the dyad of transformation. It is the unit vectors where you are going, dyad the vectors where you are coming from. The vectors where you are going, dyad the vectors where you are coming from, is the transformation dyad that will give you the answer. What do you mean by the answer? You are going from one system to the other. You are trying to find what are the coefficients of this new of your vector in the new system. What are the coefficients? So you knew the coefficients in the old system, but can you find the coefficients in the new system? The answer is yes. Just get the transformation dyad and use it to operate on the vector. It will give you all the coefficients in the new system. How do you get the tensor in the new? How do you get the dyad to operate? You take the unit vectors in the new system and do its dyad product with the old system. This one now is the transpose of it, is the other way around, because that's why if it was the correct thing, we would have said RV. This is the transpose of it. That means that you are going from, if you are going from xi to E, that will be correct. If you are going from E to xi, it will be xi circle times E. So you can see that whether it is the transformation or the reverse transformation, it is the dyad that you use to get the answer. Our time is gone. If you have any questions on this, there are things that are difficult, please post the questions in the chat room. I will still take a look at the chat room before the next class. And if it is necessary for me to send you a report, to send you an answer, I hope you got the answer I sent you last week, because there was a problem we looked at in class that there was no clear answer in class. But eventually, I sent the result to you. So let me just go to the chat room and see what's happening there, and then I'll close today's class.